Yeah.
Okay, so hi everyone. My name is Juan Guillermo Betancur. I'm a mechanical engineer, currently pursuing a master's in analytics. I have experience in the oil and gas industry and the general energy industry as well. I started out in technical sales and services, so turbo machinery maintenance, turbines, compressors, all of that, and then I switched a bit since I was also in like the maintenance side of things, and since I have had like a strong background with coding since I was in school, I decided to then like shift my gears and enter the data science domain. And for these past 3 years, I've been working mostly with industrial assets, trying to optimize them and improve industry procedures and general operation of equipment. I think that's enough of me as an intro, and now we'll get into the actual presentation. Okay, so I just want to give a brief intro about carbon footprint. Although we most know what it is, it's just any activity that releases carbon dioxide. So it can be anywhere from if you take a shower using natural gas to heat up the pipes, that leaves a carbon footprint, or driving your car, if it uses gas, also leaves a carbon footprint. And even though if you use an electric vehicle, but if that electricity comes from also like burning energy or like a fossil fuel, that also counts as a carbon footprint. And we know that decreasing the carbon footprint reduces the effects of climate change. And aside from this, like just helping the environment, some net zero emission laws have been standardized in countries and companies that by 2040, 2050, 2060, they should achieve a level of net zero emissions, meaning that they should incorporate any means of carbon capture from the atmosphere. So when they burn more fossil fuels, their net production is zero. And we'll also see how implementing AI can help us meet these goals. Also, if I'm speaking too fast, just let me know as well, because I tend to like go at it 0 to 100. Okay, so let's talk about a bit of about kilns. These are the names for the furnaces in the industry. So it's basically a contained system for burning or baking or drying, specifically in our case for heating up or calcining some materials like lime or cement. And industrial kilns are like the furnaces that you can imagine, but at really high temperatures and hundreds of meters long. And it's just huge assets that release a ton of energy. And there's a lot of requirements in industry right now to improve these processes. So let's go over the basics more or less of what, like how the kilns work and how do they look, because I'm sure that you can see three really different images that you won't think that it's a kiln or it's a furnace. So the first one, change my pointer to laser. Yep. Okay, so the first one is a tunnel kiln. As you can see, these stretch out like up to 100 meters or more than 100 meters, as well as the rotary kilns. But these furnaces are mostly used for ceramics. So anywhere from the mugs you use to drink your coffee, the plates to eat your food, to your toilets in your bathroom, all the way to electrical resistances that are in the power lines. All of these things are made in these furnaces. And these processes can take up to 40 hours. I mean, like from 24 to 40, 46 hours inside this furnace. And it's, as you can imagine, taking one of these furnaces up to, let's say, 1200 degrees, 1400 degrees Celsius, that's a lot of energy burning for a lot of time. On the right, we see a vertical alternating kiln. This is also used for lime, as well as the rotary kiln. And what's interesting about these furnaces is that when you, it's an alternating because you only power one of the sides at a time. So you can have one side burning for 15 minutes, then then you shut off one side and you turn on the other. And in the middle, you have a heat exchange from one side to the other. This helps with the overall efficiency of the kiln. And now we have the rotary kiln. Rotary kilns have a huge flame from one side that's just heating up the material that's coming in from the other while rotating. The rotation is key because this helps with the mixture of oxygen. So if it's not rotating, then you'll just get like the cover with lime, and you'll just have limestone in the bottom. So you won't be able to actually calcine all of the material. And regarding fuel, you can use gas, coal, electricity, and also recycle garbage. So a lot of times you just need a certain temperature depending on your process. So you don't need like that good of a control. So I mean, this also affects carbon footprints, but it's part of the process. And now the interesting thing about these kilns is the data. So first, let's see here. This is the rotary kiln. This is from the side here where the flame is. And you can just see it's a huge device. Also, it can be up to 150 meters long. Just imagine a steel tube up to 1400 degrees. That's hot. It's bending. It's turning. You have a lot of variables to measure. So since these are important variables, we want to sample the data in seconds or in minutes. Usually more than that, you're really losing the trend of the data. So in industry, generally, depending on the application, you can sample anywhere between seconds and minutes. Here we can see an alternating kiln as the image, and the tunnel kiln. So you can at least have a mental reference of how it actually looks like, because sometimes like that diagram doesn't really like explain how does the kiln look. And variables from these kilns, I mean, you have whatever you want, flows, pressures, temperatures, fuels, product types, masses. You have hundreds and hundreds of variables that you want to analyze as an enclosed system for your energy optimization. And obviously, you know that control systems have been in place for decades. I mean, this isn't new. And really, integrated control systems are an excellent job keeping values at their levels, knowing when to change. When you change your process, it automatically detects when it's going way too up or way too down. It uses PIDs in PLC systems. This is a PLC, by the way. And I mean, it works. And if you go over a certain value, you can have alerts, you can have shutdowns like automatically from your PLC. So these are great tools to control your kiln, but they aren't enough if you want to go above and beyond and predict. I mean, currently they have really advanced techniques, but for the sake of being able to easily implement it, it's really hard. I mean, it's easier to learn how to implement AI and having a lot of domain knowledge that I'll touch on at the end of the presentation, and be able to work with the systems. So I want to go over some of the current issues that we right now have. And you will always see this happen, that the operators in a kiln, in a turbine, with a compressor, you name it, with trucks, with coal trucks, they have a lot of empiric knowledge. So they've been working at the plant for 10, 15, 20 years. They're the gods there. They know how everything works. But I mean, humans always make mistakes, and we can't really rely on empirical knowledge to operate efficiently a furnace, especially if you want to, let's say, change a product. So if an operator was working for 10 years with a product and then a new product comes in, he won't be able to easily transfer this knowledge that he knows to a new product. Let's say the new product is really different, because if it's the same, then you may transfer some like empirical knowledge. Also, efficiencies are set with the design, like the initial design of a furnace or a kiln. So when you buy a furnace, you know how much tons of ceramic or cement or limestone you're going to produce per hour, per day. You know the material, you know everything. But as we can see, I mean, these are a bit of an exaggerations. This is a thermocouple. This is to measure temperature. This is the wall of a furnace. This is refractory material. And this degrades over time. So the efficiency that you had initially isn't there. I'm not sure if the chat is, oh yeah, awesome. So the design efficiency isn't the same over time. And it's something that you can't really know how much it is decreasing unless you measure it and unless you are able to predict it, because you can have new baselines of efficiency, or if you change products, then your initial design isn't good for your new product. So these are really things that are hard to really adjust. And as I mentioned in the slide before about the PLCs, I've seen a lot that we go to a furnace and they change the PID parameters, and this really just affects how much energy or how much fuel or gas or oxygen is being pumped to a furnace. And you can have an excess of 20, 30, 40% of energy just in one zone of the furnace because somebody changed the parameters a few years ago and nobody noticed. And also, as the images we can see here, equipment degrades over time. So once again, they're not to their original standard. We don't know if this thermocouple was actually giving us a correct measurement of the temperature, which means that the control system starts to heat up even more the furnace, so it can reach the temperature that it's sensing. So this is all a part of maintenance, planning, and prediction. So as well as having stock just sitting in your warehouse to change a thermocouple, and let's say that you have 50, 100 plants worldwide, you're not going to have a warehouse at every facility with a thermocouple with refractory material. And let's say in a cement factory, you have grinders in order to pre-grind the material. So you need gearbox, you need motors, you need rollers, you need thrust pads, you need a lot of things. And having this just like sitting around isn't really viable. Also, you can't set up a maintenance plan. So let's say that your equipment fails and you have 1 week to repair it. You just can't mobilize easily a team to an offsite location to fix a machine that, first, the parts, since they're not in inventory or are too expensive to have in inventory, you have to order, which may take weeks or months to get in. So as you can see, like planning maintenance on a short notice isn't a viable option. I mean, this is done for other kinds of industries, let's say oil and gas, where you pay teams to be sitting around doing nothing until a problem occurs, and then you fly them over. Because I mean, oil and gas industries loses in somewhere in the range of hundreds of thousands of dollars per hour. So they do have the money for these kinds of setups. But other industries that they focus on volume, as cement, as ceramics, as other materials, they focus on volume. So they can't just like waste money idly with people sitting around. And also, lacking predictive power means you can't really plan these maintenance, meaning that you have to do what's called permanent maintenance. So it's something that, or preventive maintenance as well. So you maintain your equipment or your assets way before it was actually going to fail. So again, you're changing out parts that were still good and you're losing money while you're doing this. So it's not always really viable to standardize a maintenance program every 6 months or every year, because equipment or parts of a system degrade at different speeds. So now let's move on to what Joel came for, the AI-powered solutions. So with this model, well, this and the other models that I'm going to show you, and by the way, the values are not the original values, obviously, since of confidentiality. So just as a heads up, And okay, so this model, as you can see, is a neural network, multiple inputs, multiple outputs, hidden layers with a lot of neurons. And what you can do, because I mean, it's been done. I've been there, like I've built these models before, and knowing how to prepare the data is key. But the idea is to basically feed the model with temperatures, with flows. I mean, with all of the process variable informations that variables that we saw in the previous slides, to a model to predict your quality, how much energy you're going to consume, efficiency, if you're able to actually predict it, because that one's like a bit more complicated, CO2 emissions. And the idea behind this, if you have a model that actually predicts with a decent accuracy, because in these types of industries, anywhere from 70, 80 to 90%, that's like a really high accuracy, then you can start tweaking parameters in order to optimize your outputs. Obviously, since these models learn from past data, sometimes you can really just like predict something that makes no sense. But then that's where also the technical team comes into play. Another of these power solutions is predicting your operation. So on the left side, we can see that these are different temperature profiles for carts going inside of the tunnel furnace that I showed you. So these are hours, and depending on where you place something in the cart, you will be exposed to different temperatures for different amounts of time. So you can optimize the placing of your ceramics according to the temperature that you know that it needs to receive and for how long, because depending on the time that a certain ceramic is exposed to heat, then it will form different bonds, and it needs time to actually cook and merge those bonds into place. So it's really important to actually know how this occurs. Also, and also all of this can be modeled with what we saw in the previous slide. Let's say that you want to start up your furnace, and you had a shutdown because you had a problem, or because they weren't to lunch. Let's say they actually stopped because of that, or for whatever reason. If the furnace cools down to a certain point, how much time will it take to reach its optimum point? And it really depends, because the heating, I mean, the energy expenditure that you need for a furnace is not linear. So there's no linear relationship here, because it's exponential. So really timing these moments from when a shutdown occurs to when you power it up means that you save energy, because if you know that it takes exactly 48 minutes or an hour and 20 minutes to heat up, then you can plan around that and make sure that when it reaches optimum temperature, you're ready to start producing, and not have the furnace reach its optimum temperature and hold it out for half an hour, 1 hour while you prep, because you weren't sure how long it was going to take to reach that point. And last but not least, as I mentioned before, I mean, these equipments also fail, but some of those are easier to spot, let's say in mills. So you have a mill that has to grind a lot of material, and mills have motors, and they have gearboxes. So everything's moving, everything's vibrating, and these vibrations do lead us to interesting information. Vibrations is one of the first indications that something's wrong in rotating equipment and in mechanical equipment. So by analyzing the vibrations and being able to cluster these vibrations and to identify if it's vibrating with a certain power, with a certain temperature, with a certain pressure, if it's normal, if it's abnormal, if it's something that's going to fail right now or not. So these are different techniques that you can actually use to these kinds of equipments to try to predict and prevent failure, and try to, at least with a few months ahead, know, like, hey, this component may be failing in 2 to 3 months to 6 months. Maybe we should schedule a maintenance soon and not have it either fail or waste too much money with with maintenance that doesn't really need it. And to just wrap it all up, this is the application of AI where you need data science and domain knowledge, meaning that if you have a strong background in industrial assets, in logistics, in finance, in banking, in marketing, in whatever, knowing and having that intuition that when you see data, you understand it, and knowing and having the tools, because machine learning and AI is a tool, knowing how to implement those tools is what right now not just this industry, but the world needs. Right now, people need specialized data science / machine learning profiles, people who understand the data, who understand the problem, who can speak with the technical team, who can speak with the data science team, who can speak with the machine learning team, and being able to translate, because sometimes, believe it or not, people just like don't understand how these tools work. And I've been there like a lot of times when people think that this is just like a magic box that you just put stuff in and it will automatically give a result. No, you have to understand the data. You have to know how to classify the data. You have to feature new feature new variables, engineer new features, excuse me. And this is what right now the world is shifting to: really specialized profiles that know how to use statistics, know how to use, have data science intuition, know how to use machine learning to optimize different problems. In my case, I just love this kinds of industries, and it's where I've always moved around. Also, with one of the models that I showed you earlier, I was actually, where I worked before, we were actually able to reduce energy consumption in 10% for one of our clients. And as well, for another client, there was just like data science. It wasn't actually AI, but we analyzed that one of their furnaces had a zone that was burning everything. Like, it didn't matter if it was empty, if it was full, it was always burning everything to the max. And they were just like wasting energy, but no one like sat down to actually analyze the data, because if you know how a system works, then you know how something should actually look. And like, obviously, I learned about PIDs at university. I worked with them in my previous jobs. I know how they are supposed to respond. And when I was seeing that the set points with the temperatures weren't really matching up, I knew like that something was up. And when we went to actually investigate, they had changed their settings, and they actually didn't know that because nobody sat down and actually analyzed their information. And obviously, from what I've been like saying for the past, I don't know how much time now, like what, 40 minutes? Oh my God, I'm sorry. With all of this, we can actually improve maintenance planning and reduce our carbon footprint, because obviously we can optimize our set points, burn less energy, be way more efficient with our assets. And thank you. I know it's not 40 minutes, it's that I had this from before.